Hi everyone, I'm Shawnak Shivakumar, and this is ImmunoAI, a machine learning framework that accelerates antibody discovery using thermodynamic, hydrodynamic, and 3D geometric interface descriptors. With traditional pipelines taking over 10 to 12 months, ImmunoAI enables rapid structure-informed screening of antibodies, which is crucial during fast-moving outbreaks like HMPV. My abstract is below for reference. The core question driving this project is, how can we develop accurate and efficient models for rapid antibody discovery? I hypothesized that training gradient-boosted models on physical interface features could capture binding affinities better than sequence-only approaches. This was motivated by a serious therapeutic gap. HMPV causes over 473,000 hospitalizations globally, with no antivirals or vaccines available. In early 2023, it was the dominant respiratory virus in children. I got motivated to work in this project after learning more about the transformational work done by the 2024 Chemistry Nobel laureates to predict protein structures. I saw a gap between fast sequence models and slow physics simulation tools and designed ImmunoAI to bridge that gap. Reviewing the related work landscape, we see sequence-based models like Antibody, which are scalable but ignore 3D structure. Physics-based methods like Haddock and MD simulations are accurate but too slow for outbreaks. AlphaFold2 as a tool is transformational, enabling structure prediction even for novel variants like HMPV 8.2. And finally, LightGBM allowed me to model nonlinear structure-affinity relationships effectively. By combining these tools, I built a hybrid pipeline that is fast, scalable, structure-aware, and grounded in immunological reasoning. Here's the workflow. First, I curated a complete set of antibody-antigen complexes. Secondly, I extracted meaningful 3D features like SASA, hydrophobicity, and H-bond counts. Third, I trained a LightGBM model on this tabular data. Fourth, I fine-tuned it for COVID-19 for broader generalizability. And five, I used AlphaFold2 predicted HMPV mutant structures for in silico screening to find the right antibodies. The goal is interpretability and speed while maintaining relatively high accuracy. I reviewed several training datasets, then selected 213 high-quality complexes from a peer-reviewed database called the Structural Antibody Database with known affinities in 3D structures. Affinities were normalized using the Chung-Pussov equation. Chains were parsed individually, and features were computed for both the paratope and epitope binding regions. The training I used was a 90-10 split with antigen stratified sampling. I optimized LightGBM parameters like learning rate, leaf size, and regularization to minimize RMSE. These plots show the spatial reasoning behind the features, like SASA, radial depth, hydrophobicity maps, and Voronoi partitions. These overlay key metrics like flexibility, and together they create a high-resolution fingerprint of the interaction surface. Additionally, the model is guided by key mathematical functions, including the negative first-order gradient of the loss, which helps compute pseudo-residuals and update model weights during training. This allows LightGBM to optimize affinity prediction step by step with high precision. Since the HMPV 8.2 structure wasn't published, I used AlphaFold2 to predict it. Validation shows strong confidence PLDT scores were above 80% and high sequence identity across conserved binding regions. This allowed ImmunoAI to screen antibodies before experimental structure was available, which is a major advantage in outbreak response. Early model performance was poor. Median true antibody rank was at 132. However, after tuning LightGBM hyperparameters, the improved model achieved an 89% reduction in candidate search space and a 30% sensitivity within the top 10 predictions. This shows that geometric and physiochemical descriptors can actively and effectively capture the binding landscape. To improve generalization, I applied transfer learning with 117 COVID-19 antibodies. After fine-tuning, RMSE dropped from 1.70 to 0.92, which is a 46% decrease, and high-confidence predictions rose from 60% to 80%. Feature importance analysis showed that hydrophobicity and hydrogen bonding were the strongest predictors, which were consistent with known binding energetics. The final model was tested on HMPV 8.2. It identified two optimal antibodies with PDB code 6W16 and AE2U, both with predicted affinities in the picomolar range. 6W16 targets the mutated G42V site, where 8E2U targets a conserved region. Both scored in the top 2 percentile of all candidates from PDB that were screened with ImmunoAI. Hydrophobicity and H-bonds emerged as the top predictors of binding affinity, which aligned with literature on binding energetics. The model's focus on SASA and APD and interface descriptors reflects experimental observations from affinity maturation studies done by Eckert in 2011. And additionally, tree-based methods like LightGBM also offered interpretability and are known to outperform deep nets on smaller datasets under 1,000 examples, as shown by Yang et al. In 2023. There are limitations, however. First, there are no MD simulations, so loop flexibility and induced fit are ignored. And secondly, AlphaFold2 predicted structures may have low confidence scores, which makes our model sometimes inaccurate. These are addressable in future iterations of dynamic modeling. In summary, ImmunoAI demonstrates that 3D descriptor-based ML can accelerate antibody discovery to repurpose and triage promising candidates. It also effectively prioritizes antibodies for the HMPV A2.2 mutation, targeting both mutated and conserved sites that can be tested experimentally. And third, it's built entirely with open source tools like AlphaFold2, PyMol, PDBFixer, and LightGPM, which means this pipeline is fast, modular, explainable, and adaptable. Next steps include experimental validation of this antibody and integration of MD simulations and developability metrics so that in silico predictions computationally can translate to real therapeutic leads. Below are my references. Thank you so much for listening.